So today we are going to talk about simulation dynamics. This is to follow up on our discussion last time of doing the setup of the simulations. So this will be a continuation of our ongoing discussion of that in our three-part series. And if we can advance the slides, there we go. And so simulations come in a hierarchy of complexity. Today, we are going to talk about the simplest kind of simulations, which is molecular dynamics of the hard spheres, which you've seen from your readings. But of course, nobody's really actually interested in running molecular dynamics of hard spheres because that is the simulation of basically ideal gases. However, these are incredibly useful simulations to do because these simulations bring up many of the ideas that will come up as we're talking about more complex systems. So the hierarchy basically goes from studying molecular dynamics of the hard sphere gas particles. The next level of complexity would be to add in what we call the soft spheres. So in fact, actually you have those readings available to you, although they're not actually part of this class. But I would encourage you, if you have time, to take a look at that because it does nicely explain how we would move from hard spheres into doing soft sphere studies of gases. And then, of course, we would move into molecular dynamics of solvated biomolecules, which is what we're actually interested in doing. So we talk about the hard spheres because in a very simple way, it explains to us the fundamental things we need to understand about molecular dynamics simulations, or any simulations for that matter, in order to move up to doing the more complex ones of more interesting systems. So then, what is the MDHS, or the molecular dynamics hard sphere model? Well, so the important part of this is the potential energy. That is really the part that defines what kind of simulation is being done. So in a very simple way, basically hard spheres behave as you would expect billiard balls or pool balls to behave. They are solid objects that cannot overlap. And so what we have here is our potential energy function that describes how they behave, which I've depicted for you in some of these diagrams here. So basically what we're following is the distance between these two spheres. And notice that the diameter of the spheres is going to be 1 sigma. So then when we look at the distance, we measure from the center of one to the center of other. And that gives us also a distance of sigma, assuming that they are the same size. So for simplicity, let's just assume that they are of equal size and mass. So what we will get then is that right here at this point, this sigma, when the two centers of these spheres are 1 sigma or 1 bond length away, that is when we will have this interesting thing occurring. This will be where the potential energy then is going to go up to infinity, because as they begin to overlap, well, that doesn't usually work so well for solid objects. They do not like to be in the same place. And so the potential energy goes straight up to infinity. So what we see here is we see a trace of, in fact, actually 2 different potentials, and that's because we are also considering what happens in actual atoms, which is where we eventually want to go with this. So in the hard sphere, there is in fact only 2 options. Either the potential is 0, meaning they're not colliding, or the potential is infinity, meaning that they are in contact with each other. And that is what this arrow is here. So when we transfer this to studying atoms, as the atoms come too close, their potential also goes up to infinity, but you see that there is a possibility to have a little bit of compressibility, but this potential function goes up quite fast because electrons also do not like to be in the same space. And then as we go to a longer and longer r, so we use r again just as our generic coordinate to represent x, y, z, as the centers of these move further and further away, then the interaction between our atoms is going to be not very much, because they will eventually be too far away to consider them to be, quote, bonded. And so they're actually at some point not really interacting at all. And we have terms in our force field equation, which I will show you later on today, which handle things that happen at short distance and also things that handle at long distances. So the kinematics of the hard sphere model is going to follow the elastic collision. So, so in this area, then we're going to have conservation of the linear momentum. That is m1v1 equals m2v2. If the masses are the same, then the mass just becomes m. So the total of these will need to be the same. We would also have conservation of energy, and in this case, because they are just rolling balls, that really just means their kinetic energy, which is 1/2 mv squared. And we have this for velocity 1 and velocity 2 of each of the particles, again, assuming the masses are the same. And so the beginning total kinetic energy has to be equal to the total end kinetic energy. And then we can write the velocity in terms of the unit vectors I, j, and k. Now you may have come across these unit vectors in your linear algebra class, and this is about resolving things into the x, y, and z components, which follow the I, j, and k. So each of those is equal to a unit of length 1 in each of those directions. And so what we can do is we can resolve the components into each of the 3 directions, and then the problem can be solved quite simply, because then the transfer of the momentum can occur in a very simple way. That is, we simply just exchange the velocity from one to the other when the mass is equal, which makes it very easy. So as I was saying, for equal masses, we can simply just swap the components in the direction where the collision occurred. So assuming that the collision occurs along one of the major axes. So here, this is occurring along I, so this is X, for example, right? All you need to do is you just need to swap the components, and then the other directions, initial and final, remain unaffected, so they are equal. So what we can do then is we can apply triangle trigonometry, which I'm sure you have seen from some geometry classes and so forth, or physics classes. What we can do is we can take a vector and resolve it into its x, y, and z components, which here are being represented in the I, j, and k vectors. And then whichever components, I and j, j and k, or k and I, may be involved in that particular collision, then we can simply just transfer the momentum in line with the axis that was affected. So you swap out the x's and the y's if those were the ones that were involved. And so it actually makes it really quite simple to do. And in fact, in some longer versions where we're focusing just on molecular dynamics simulation, we actually do the exercise where we actually calculate this out and can write up a little program to do exactly that algorithm. So one of the things we need to do then is we will need to solve the quadratic equation with the limiting triangle. And what this is about calculating when the next collision will occur, right? So this is based on the Pythagorean theorem, and you may recall that that includes the discriminant. So we have 2 roots, right? Because that's an equation that goes in x squared. So that means there will be 2 roots. And you might have a real and imaginary root, or you might have 2 real roots, or you might have, I mean, there's all different combinations of how that can work out, as I'm sure you've done in your pre-calculus class. And so basically it's where your parabola is going to cross the axis, and if it doesn't cross the x-axis, you'll get your imaginary roots, and you of course could have 2 of the same roots. That's a possibility. And so what we are interested in doing is we're interested in the shortest route, right? Because that means that will be the location of the first collision, which is really the one we want to look at, right? Because if you solve for the long route, the problem is that it will have already collided and should already be moving off, because of course that's what would happen in real life, right? would collide on the near side. So we call this the limiting triangle because what we're doing here is we're calculating the angle at which the these balls are going to graze each other. So any angle that would be inside of that would then, of course, result in a collision. So what we need to know is we need to know what will be the time to that collision. And so then we calculate the time to that collision, and that is how we'll know how long we need to make our next time step in the course of the simulation. So we have to do this between all of the pairs, and that is what we use in order to make our collision table. So in the collision table, what we're going to keep track of is all of the pairs. So we need to have the neighbors, and we have all of the pairs, and we roll the balls forward in order to figure out when the next collision will be. So we do this. We calculate the delta t to the shortest one out of all the possible combinations, because that will be the next collision. Knowing the delta t, then we'll roll forward all of the balls that delta t, and then we will calculate the effects of the collision and move them on to their next course. So that's the general thing that we do. However, we need to also remember that there could be collision with the images, right? So remember we talked about the periodic boundary conditions. So if we're going to have that the particles could potentially interact with their images, then we need to also compute that. So for example, in this case illustrated in this unit cell here, notice that the next collision will not be with the particle that is in its own box. The next collision will be with a particle in the neighboring box, the image. And so what we need to do is we need to make sure that we are searching not only for collisions within the unit cell, but also if we are having collisions with a neighboring unit, so that we can use that information to correctly update our tables. So this brings us to the simulation algorithm, which I've mentioned in brief, but let's just take a look at this in a little bit more detail. So when we're going to begin the simulation, there are going to be some choices that we need to make. So for example, we will need to do the initialization phase. So one of the things we need to do is we need to choose the number of particles n that we will need in order to carry out the simulation. We also will need to select the density of the system. So if you have studied physical chemistry, you may have seen lots of information about the density of systems, because this is one of the important physical properties. This is also referred to as the packing fraction, and what we mean by that is typically a hard sphere packing. That is, how closely can we pack the atoms together? You may see this in, for example, discussions about solid crystalline substances, such as if you do geology studies and these kinds of things, you will see that that becomes important. But for our purposes, the density is basically just the packing fraction. That is, how closely together are we going to place all the spheres. Then we need to figure out how to set the initial positions of the coordinates. So you might say, well, how should we do this? One way to do it might be, well, let's just have a box, and we will simply just randomly put the positions in the box. So if we have n particles, we'll roll the dice n times and put the particles in the box. However, can you think of any potential problems with that? Well, one problem with that is that the positions may overlap. And that would be bad, because we said that the potential energy for that is infinity, and that would mean that our system would blow up. So that's not a good idea. So another way that we could do it is we could put the particles on a lattice. So oftentimes we think of a crystal as having a lattice. So for example, think about sodium chloride, table salt, the stuff you have on your kitchen table. that you sprinkle on your food, right? You have a sodium and a chlorine, and they alternate a sodium and a chlorine, and they go in a regular order, and that is what makes them have that crystalline shape. That's why if you actually look at a grain of salt, it tends to be actually kind of a cubic, and that's because of the underlying molecular structure of the salt particles. So what we could do is we could choose to regularly place our particles on a grid just like would occur in a crystal, because that would mean that they would all be far apart enough so that they're not going to overlap. It would guarantee that they won't overlap, and that could be really great because we will not have the blowing up problem. So that's what we would need to do. But of course, if we put them on a lattice, then the issue becomes, well, that's maybe not actually how the particles really are. And that is a major reason why we need to do the equilibration and so forth in order to get the simulation started. So we'll have the particles on a lattice. Sounds like a good idea. One of the things we need to do next is we need to assign the velocities. So how shall we decide to initialize the velocities? Well, one of the ways we could do it is we could just say that we could just divide them in half and say all the particles on this side are going to move in one direction and the particles on the other side will move in another direction. Well, yeah, it will work. However, it may take a while for the velocities to equilibrate. So what do we mean by that? Well, if this is supposed to model a gas, then that means that the motion of the particles should be random, which will happen eventually as the particles collide with each other and the velocities get transferred. You will gain a distribution of the motions of the particles, and you will also get a distribution of the velocities. So incidentally, this is exactly how we get temperature, right? So temperature is a measure of the kinetic energy of the gases. So just to call to mind the kinetic theory of gases, that says that the temperature in the room is the measure of the average velocity. Well, let's say it's proportional to the average velocity of the particles. And so when you measure the temperature, you're in fact measuring the average. That means that some particles are going to be a little bit faster and some particles are going to be a little bit slower. So when I teach physical chemistry, I illustrate that to students by asking them to consider a pot of boiling water. Maybe you want to cook some spaghetti, and you put a pot of boiling water on the stove. Well, if the distribution of kinetic energy were not true, what would happen when the water reached the boiling point? Well, all of the particles being at exactly the same temperature should reach the boiling point at exactly the same instant. So what would happen when you reach the boiling point is all your water would spontaneously all become a gas. It would all evaporate all at once. And thank goodness that doesn't happen, because if that did, you wouldn't really be able to heat up your spaghetti very well. So what we can say is that as we are heating up a pot of boiling water, is that some particles may become in the gaseous phase sooner. That's when you start to see a little bit of steam coming off the surface. You may see some bubbles forming at the bottom. And then as the temperature rises, some particles will begin to boil. So there'll be an increased number of bubbling, right? So what is happening when the bubble forms is that some waters are losing their intermolecular forces and going into the gaseous phase, which usually happens at the bottom of the pot because that is typically where the heat source is located. And then the water bubbles up. But it's happening over time, right? And so there's a distribution of water molecules, some of which are colder than the average and are moving less and remain in the liquid form. And there are some particles which have higher than average kinetic energy and are escaping from the surface tension of the water up into the atmosphere, just into the air. And that is how boiling occurs, and that is why we have a distribution of the velocity. So this will become important when we take a look at the H function, which shows us that we need to have a distribution. And when we are trying to run our simulations, what we are trying to emulate is having that distribution of energies of the particles so that we can model what actually happens. So back to our algorithm here, so we need to assign the initial velocities to replicate that distribution, either by assigning them off of a distribution to begin with, or doing something kind of silly, such as having all the particles move in one direction or another, and allow the, the randomization to occur as a result of the collision. So the best thing to do is to have the particles moving in more random ways to begin with, such as assigning them off of the distribution, which is what we do when we run molecular simulations. Then we'll need to make our table of the collision times to know when our next collision will occur, and that is how we initialize our simulations. So equilibration, this is what we'll do. So from the collision table, we're going to figure out the delta time, the dt, to the next collision, and identify which collision pair will be colliding. We advance all particles by dt. We apply the periodic boundary conditions for any particles crossing the unit cell boundary, just to make sure that there are not any particles there that are going to collide sooner. We are going to apply the elastic collision physics to obtain the post-collision velocities for the colliding pair. Then we will update the collision table. If there are any properties that we're interested in computing, we will compute those properties. Oftentimes we're going to monitor some equilibrium properties, such as the H function and the packing fraction, and any other properties of interest. So there may be some problem-specific questions you want to ask, and you can compute those at this time. And then we would repeat the steps until equilibration is satisfactorily reached, which I am purposely leaving a little bit vague because we will talk about that in more detail momentarily. Then we get to the dynamics. So from the collision table, we want to figure out the dt to the next collision. So it's basically, it's the same thing, right? We repeat the same thing, except that we're going to compute the properties of interest, which may now be different since we're in dynamics and we're not waiting for the equilibration to occur. So we don't need to keep calculating the equilibration parameters. So then we can compute the actual properties of interest for the study at hand, such as studying the molecular motions, allosteric, drug design, many other things. So we would then collect that information from the dynamics portion, and then we would repeat the steps for the desired simulation time. And we will talk about when is my simulation done momentarily. So as we were mentioning, we may choose to have the initial positions using a crystal lattice. This is a depiction of a lattice of particles of two different types. So this is an example of the lattice type that's used for sodium chloride or common table salt. Forms a cubic cell unit, and so we could take something like this and replicate this to guarantee that our particles will not overlap. So how do we know that equilibration is, quote, done? Well, the answer is there's no real way to say this is not done and this is done. But we might say that we've reached equilibration with respect to a particular point of interest, and that is generally what we want to do. So one thing that is very useful is we want to watch for the decay of the regularity of the lattice. So when it is in the lattice, it is in the solid form because the interactions are very high. So the regular placement of the molecules or the particles. Of course, in an ideal gas, there is no interaction between the particles, which is what our hard spheres are doing. Real particles, like real biomolecules, of course, do have interactions. And so what we would do then is we would want to wait for those particles to move off of their initial position. So what we see here is the order parameter is going to be related to the entropy distribution, which makes a lot of sense. So basically, as the order or the position of the particles is changing over time, then what we see is that we have the order parameter of 1, right? So if you work out this equation, we see that the equation will go to 1 when they are located very close to all the same position, right? So the expected position is those lattice positions, and as they move away from those lattice positions, the distance between them becomes larger, and so the order parameter will decrease. So what we're typically looking for is this initial drop off. So the particles are going to move away from their initial position, and then we are going to have this equilibration phase where they are changing rapidly and trying to work out the velocity distributions and so on. And then we typically go into this production mode where we have a fluctuation or oscillation between some limiting values. So this is what we watch when we're doing the hard spheres. In regular molecular dynamics, the corresponding metric would be root mean squared deviation, which is instead of the order parameter, which is related to the position of the atoms, we in fact actually calculate the position of the atoms based on their actual initial positions and look to see that they have moved from that and how they are fluctuating around those initial positions. The velocity distribution and the H function are related in an important way. The H function is going to be what is going to measure how similar the distribution of the velocities are. So this is why I was telling you about the kinetic gas theory. So the kinetic gas theory states that the particles should be making a Gaussian distribution. And so the idea is that our velocities should be making a distribution. And so what we do is we bin up the velocity values on the x-axis. So we make a series of bins here, and then we look to see and we count how many particles are in each of these bins. And so the number of particles should be close to the expected number using the Gaussian equation. So what we can do is use kinetic gas theory and the Gaussian function, and we can work out what the height of this curve ought to be. This is our ideal curve. And then we count up how many particles we actually observed at these points and ask the question, how similar is this to the actual distribution? And so then the H function will be related to this. And so what we see is the actual decay, right? So this is the collision number, and the particle distribution is going to become more and more like the Gaussian distribution. So you notice that, so there is some transformation that occurs between the distribution and the H function that's being plotted over here. It's a mapping function, which I am being a little bit obscure about because we actually don't do this in regular molecular dynamics simulations because we do generate our velocities a little bit differently. So we won't get into that too much because it's a bit of a less important point for the main ideas here. So what we see though is that we would see some jagged lines, and this is, as we can see, the number of collisions going on, and as that occurs, this distribution is getting closer and closer to the random distribution that we see when we would have a Gaussian having evolved. And if you don't have that distribution, that's how you know that your velocities are not have not equilibrated yet. So like I said, in regular MD, we don't really do the thing where you would start with all the atoms moving in one direction and all of the other atoms in the other half of the box moving in the other direction. So we do it in a bit more of an intelligent way. We actually have the distribution, and what we do is based on the probabilities of this distribution, we assign the velocity. So they need to equilibrate in terms of the momentum because the masses, of course, of the different atoms are different. So we need to have the equilibration work that out, but that in fact actually relaxes really quickly. And so our equilibration deals with a lot of things such as the position of the waters on the lattice because we solvate our system. And the problem is the waters tend to be stuck on the lattice, which means it's ice. And that's not very interesting for biological systems because most things are not frozen. So what we're looking for is mostly for the waters to melt in the lattice, that is for the positions to move away from their initial positions, which is what you get when you have a liquid. They're still nearby, but they do not form a perfect lattice, and that is what gives rise to the liquid properties. So in gases, we have this non-ideality, and this gives rise to the virial or Z. And so we are going to use this as one of the metrics that we can look at for our hard spheres. So because they are not compressible, one of the things that we could do is we can calculate this Z value. Now you may remember the ideal gas law, PV equals nRT, which is basically this is just rearranged here. PV over N, and then your gas constant is being represented by K here, so nRT, where N is the number of particles in your system, being represented as the large N for Avogadro's number of particles, a very large number of particles. And so basically, what we do when we are doing the virial is we ask ourselves, in order to get the answer of what we do actually have for PV over nRT, what fudge factor would we need to make this actually correct? That's essentially what's happening here in the virial. And so that gives us the non-ideality of the gases, which from physical properties arises from the fact that gases in fact do interact, because gases are not totally inert, and they have electrons, and they're not actually spheres, and they're not point masses. So that is where the non-ideality comes in, but the virial, that measure of that non-ideality, can be used to tell us important information about the gases. And in physical chemistry, we have several chapters on just this topic, where we try to understand how gases behave, and then we can from there extrapolate how liquids behave, and how solids might behave for being extremely not ideal gases. But that is how we have built up our understanding of how particles interact. And so that brings us to the phase diagram. So in a phase diagram, what we're going to do is we're going to study the basically the non-ideality from the pressure versus the packing fraction, which again is just how closely together the molecules are. So here we will see that we will have the fluid and the solid branch. And so how this curve between the different phases appears will give us information about the relationship between those various things. Now, when we do molecular simulations, we're really talking only about the fluid dynamics. So we don't really do a lot with changing the pressure and the packing fraction, because in MD simulations, we're usually in the liquid phase, and liquids are really not very compressible. However, the box size can change, and during equilibration, we do allow that to occur. And so it is, to some extent, somewhat relevant. So then one of the things we need to do is check the reliability of the code. So this is really in the development phase of the code. So the AMBER simulations have been around since the 1970s, which is a pretty long time. So in day-to-day use, we don't really check these things ourselves too much. We pretty much trust that in the past 50 years that people have gotten those kinks out, which for the most part they have, and all of these things are well documented and have been done over the course of many PhD theses and many other studies. But in terms of actually developing the code, these are some of the things that one would think about. So in the equilibration, we want to check the position and order parameters should be fluctuating about 0, with the fluctuations having a magnitude of plus or minus root n over n. So I didn't go into the derivation of this root n over n, but this is again something that comes from physical chemistry and the ideal gases, and this can be derived from the ideal gas parameters. The kinetic H function should approach a value consistent with the Maxwell distribution. So basically, we should see that when we have the Maxwell distribution, we compute the ideal H function, and then we also compute the H function from the data that we have, and we compare the two, and that's how we decide if we have equilibrated the velocity. So basically, these two things are checking the equilibration of the positions and the equilibration of the velocities, which for regular molecular dynamics simulations would be equivalent to that the starting structure has relaxed from the X-ray crystallography molecular crystal structure, and that the velocities are okay. So we don't check the velocities as much as the positions, but we do check for the waters. Then we would also want the conservation principles to apply. The number of spheres in the primary cell should be constant with time. So that would be very bad if they started disappearing or you got more in. There is such thing as simulations where N changes, but usually that's a gas kind of a simulation where you allow the pressure and the volume also to change. Each Cartesian component in the total linear momentum should be 0. So otherwise, it means you have a net movement, and so you're not at equilibrium, so you should not have it. And the total kinetic energy should be constant with time. So constant energy simulations stands to reason that we should have the kinetic energy be a constant. When we were talking about the Hamiltonian last week, we talked about the energy being the same. So in this case of the hard spheres, we only have kinetic energy. So that means that the kinetic energy for hard spheres has to be equal. And also the kinetic energy should be equally partitioned among the 3 Cartesian components, meaning the X, Y, and Z should all be about the same. So otherwise it would mean that your gas or your particles have some directionality, and that wouldn't be equilibrium either. And for values properties, we want the instantaneous property values to be stable, fluctuating about constant values, which also we have in regular MD, and averages should be reproducible with statistical uncertainties when the runs are repeated from different initial conditions. So that is something that is very relevant to regular MD simulations, and is something that we test with a number of statistical tests, such as the Chapman-Kolmogorov test, on a regular basis. We'll see this when we get to some of our final exercises when we are looking at MD-based Markov state models. So one of the things we want to do is check the statistical significance of an event. So we have a full phase-based trajectory, meaning over, like, we could run the simulation for an infinite amount of time. What we could do is we could divide our trajectory into a number of segments, and then we could divide that further down. And so what we can do is we can compute averages over the smaller pieces. Now, if there is an interesting event, what we would like to see is we would really like to see that event occur 3 times. So what we can do is we can divide up our simulation into pieces, and we can ask the question if we see our event occurring on multiple times. So in molecules, what do we mean by an event? Well, it means something such as maybe a bond, maybe there's a particular interaction that occurs that's meaningful for biology. If it happens just one time, we don't know if we just got lucky and we sampled that right in the beginning of our simulation, but it's really very rare. Or we don't know, like, is this something that happens and does and undoes itself all the time, right? So what we can do is we can divide our trajectories into chunks, and then take the average properties of those chunks and ask the question if the averages between the different chunks match up. And that is actually at the heart of the Chapman-Kolmogorov tests for convergence of the simulations, and also for hidden Markov models that one might actually make from them. So why should we run simulations longer? Well, the reason for running simulations longer isn't to get better accuracy, because that's going to be limited by the code. It's actually to decrease the statistical uncertainties. And basically, as you can see, they're following some particular property here. We're following the virial again. And so what we see is that the uncertainties are quite large, but as we run the simulation longer and longer, those uncertainties decrease, and that's because we are seeing events more frequently, and so then we have less uncertainty about the time scale between those events. So what we really want to do is ideally to run the simulation a minimum of 3 times longer than the time between the interesting events that we might want to observe in order to have good statistics. So we might want to try to detect systematic error. We can apply the chi-squared test in order to do this. You may be familiar with chi-squared test from a statistics class, or perhaps some other classes. You can use the chi-squared test to check that a given distribution fits a particular distribution, and in the Pearson's chi-squared test, this is going to check for the normal distribution about the mean using the Gaussian. So what we're going to ask with this test is how closely does an observed data fit the expected data pattern, and this test can answer that at various degrees of freedom. So of course we would like it to work well. We also have the thermodynamics limit that we need to take into account, and so this means we need to extrapolate to an infinite number of particles. Of course, we don't have an infinite number of particles, but we would like to presume that we're saying something about when we had an infinite number of particles. Otherwise, we're simply just reporting on how the particles interact with their container or the artifacts of working in a small simulation. So of course, more sampling is always better. So what we can do is we can study the limiting case, and generally that's taken to be as we go to 1 mole of particles, which is Avogadro's number. And that is too large to actually simulate, so oftentimes we try to get information about as large of a system as we can practically study, and from there we are going to extrapolate to the larger system. So incidentally, Avogadro's number is 6.022 times 10 to the 23rd, which you might recall from your Gen Chem class. And that number was chosen so that the mass of 1 mole of a chemical compound in grams is numerically equal to the average mass of 1 molecule of the compound in Daltons, which is just a very convenient thing, but also it tends to represent our idea of what it means to have an infinite number of particles. Incidentally, in fact, that number is kind of small, and 1 Avogadro's number of water molecules would easily fit in a teaspoon as a drop of water. Fun fact. The thermodynamic limit in practical considerations then can be done by, as we said, running things for smaller n's than actually there are. And this is using a linear fit to the results that one gets in a simulation, and then we can extrapolate out to the number of particles of interest to use that linear relationship. What we do in regular molecular dynamics simulation is typically not to add more particles. So our particles being, say, like a protein is pretty difficult to simulate as it is. So we can't have multiple copies of the protein. What we tend to do is to work with the periodic boundary conditions and so on, and make sure that we have a lot of solvent around it so that the interactions are with the waters and not with other particles, which would make it be more dense than it actually is, and also to simulate being in this bulk solvent, which is what we assume happens as we have a larger and larger system. So for development of the simulation code, of course, reproducibility is very important. So these are some of the things that have been done to make sure that the code is working. And if you happen to write a program from scratch for simulation, some of the things you should do. Repeat the runs using the same code on different computers. Repeat runs using the same code, but different compilers. Repeat runs using the same algorithm, but different code. So for example, have more than one person run it. Repeat runs using different algorithms, and repeat using different simulation methods. So you might do molecular dynamics in Monte Carlo, or you might run your simulation using the AMBER package and the CHARM package or the GROMACS package, and ask if you get the same results. So many of these things are the things that have been done with the AMBER simulation package, which convinces us that...
Professor?
Yes?
Would you also, like, what about going in between different, like, force fields? Is that an effective method, or?
Well, when you switch between the different packages, you're also effectively switching between the force fields. Developing a force field is probably the most challenging part of doing the simulation of biomolecules, period, and has definitely been the focus and continues to be the focus of active research to improve the force fields. So one usually can't afford doing it in a different way, but what we can say is that there have been two major independent philosophies on developing force fields, the top-down approach and the bottom-up approach. What we mean by that is basically the CHARM versus AMBER controversy in the simulation world. So if you do a top-down methodology, what you do is you start with knowing some property and what it ought to be, and you work out the parameters within what we know about how molecules interact, and fill in the numbers and to make it be what we expect, and then we assume transferability to other molecules. So that approach tends to do extremely well when you're using molecules that are very much related to the molecules that you have used to parameterize it. However, it can suffer from overfitting. Now, the opposite way to do it is to do a bottom-up approach, which is the AMPER approach, and that is what Peter Coleman pioneered. We said, let's start with physics. So you can only write it in if it's known in physics that this interaction occurs, and we're going to use the values we get from physical calculations, and we're going to hope it gives us the right answer. So at first it didn't, but we have now 40 years later, it's a lot better, and basically gives the same answer that CHARM gives. So this gives us some degree of credibility that the force fields are more or less doing the things that they do. And so there are people who use only one kind of simulation or the other, but that is why we have both of them. And for all intents and purposes, actually, you can use either one. I've done research with both of them, and they're both quite good.
Okay, so that does mean that probably you could try the reproducibility of runs by just switching between force fields.
You would switch between force fields by switching between packages. So you're not only just swapping the force field, you're also swapping the algorithms that go with them because they're not compatible. But basically, yes, that is how that test could be done.
Okay, thank you.
Yes, good question. So then we want to consider, coming back to the idea of, why are we studying molecular dynamics of hard spheres? Isn't it all about ideal gases, and who cares about ideal gases? That was over, 200-300 years ago, who cares? It's because there are many things that are really actually quite useful about the MD hard spheres, and hopefully is helping you think about how simulations are done. So the major differences between the hard sphere and the regular dynamics are talked about the force field. So infinity versus zero, the MD hard sphere, versus actually building in what the force field is, which I will show you in a sec. We also have the time step. So we talked about collision time. Now that's not really going to be relevant anymore because we're going to need to have some time because there aren't collisions when you have soft spheres. And the algorithm for the dynamics is somewhat different. We talked about the algorithm for the hard spheres. It is essentially the same in terms of the qualitative ways of talking about it, but the actual implementation of it is really considerably more complex, which is probably not that surprising. And also just the set of complexities, there are a few more steps that we would use in actual MD simulations than we talked about with the hard spheres, although again, we can see hints and clues as to how one would do this from the hard sphere counterpart. So this is what the force field actually looks like. This is the basis for the AMBER force field, and also the CHARM force field basically follows a very similar thing. GROMACS and the others also pretty much follow this. And generally what is different between the force fields is how we arrive at the parameters that go in between these. So the components that we have are the bond stretching. That's how long the bonds are between some atoms, which is this term right here, which looks a lot like Hooke's law because that's basically what it is. The angles also are going to be involved, and that is the angle that is made between the atoms. Again, follows a Hooke's law. So basically we're talking about a compressibility of this angle right here. Torsion, so what we mean by the torsions is the 1,4 potential. So notice that this is also known as the dihedral angle. So just in case you're not familiar with the dihedral, notice that these 4 atoms are related to each other. So you need 3 points to define a plane, right? So here is our first plane, I, J, and K. And then from there, we can also define a plane, J, K, L. And so then we have 2 planes, and we can look to see what the angle between those planes are, and that's what a dihedral is. So this is going to be similar to Hooke's law, but this has some rotational components to it. Then we also have the non-bonded interactions, and those are things that are not involved in, as the name suggests, in the direct bond atoms. So the simpler of the two is this term right here. This is Coulomb's law for the charge interaction of two particles. And so like things attract, and I mean, no, that's wrong. Opposites attract. So plus and minus charges will attract each other, and things of the same charge will repel. And this will depend on their distance from each other, which is the Rij term, and it will be screened by this epsilon 0, which means, for example, if there's stuff in between, then it will not feel the charges the same as if there was nothing there. And we have some components for the spherical nature of the interaction. The final term that I didn't mention is this Leonard-Jones term, which is something that's a little bit too advanced to get into in this particular class, but basically it is following the same kind of a potential like we saw over here. So when I showed you that well potential, it's essentially that. What it's saying is that there are some interactions that occur because of the quantum mechanical effects of electron clouds. And because of that, we get our bond, our equilibrium bond length. And so what happens is you will have atoms wanting to be at a particular length away from each other, because that's how their electron clouds optimally interact. And if you compress them closer than that, they're unhappy because the electrons are bumping into each other and they repel. And if you pull it apart, it's too far away to get an interaction. And that, in a nutshell, is what happens in the Leonard-Jones term, which is being simulated by the difference of two functional parts here. And so that is how we get our force field, because those are the major known interactions that occur between molecules. And as you can see, it's more complicated than yes or no, the infinity or not. And the soft sphere potential would be something in between, where you could choose typically either the Leonard-Jones or the Coulombic term is chosen to do a simulation of gases to understand how they interact. Yes, and they all have their little boxes for their pictures. Okay, and so the other thing we need to think about is the time step. So when we did the hard spheres, we had our lookup tables, but collision doesn't really apply anymore. So we need to select a specific delta t. So we typically take a 1 to 2 time step, 1 to 2 femtosecond time step for simulations, and our simulations typically run from hundreds to thousands of nanoseconds. So a typical setup would be a 2 femtosecond time step, meaning you roll the particles forward for 2 femtoseconds, and then you add up those femtoseconds to make the nanoseconds, and then this is equal to about a microsecond, which is a reasonable state-of-the-art limit. I mean, we can actually run things longer than that, but typically one would, as a rule of thumb, want to run something out to about a microsecond of time these days. And also thinking about applying some of the rules we were looking at to see, you know, is my simulation done based on the property of interest. We're using the simulation algorithm as implemented in Amber. This is a molecular dynamics package, which you've already encountered. You used TLEAP last week, which is part of this. This is the assisted model building and energy refinement package. The Sander, which is the essential simulation algorithm, this is where it's written in, is simulated annealing with NMR-derived energy restraints, because historically that's actually how it got started. People were trying to solve NMR data, which actually gives you distance constraints between different atoms, and then you try to figure out, well, what structure must it be in order to fit those distances, and that's actually how it got started, and how these simulations were built up. And finally, we have the PME-MD, which is the CUDA-enabled parallelized version. This is the particle mesh Ewald molecular dynamics. Particle mesh Ewald is a way of summing up the electrostatic charges. We talked some weeks back about calculating the exact interactions within a certain distance, and then beyond that distance, using just a generic value, which will speed it up. Because the Coulombic term needs to be calculated pairwise, meaning between every single atom in the simulation, no matter how close or far away it is. That is by far the most expensive calculation to do, whereas the bonded terms, you only need to calculate to the things that are bonded to it, so you don't have very much to do. But you can see that particle mesh Ewald has made it a lot better, because being dividable by these, because you can divide up your box distance-wise, and then you can apply your cutoff. You can then take that and parallelize that by sending off different chunks of your box to different machines to do the calculation, and then compile your answers back together on that Coulombic term, which is the one that's most problematic for actually getting your simulations to finish. And so that was what has really made things much faster. And because GPUs are so great at it, that's why PMEMD is now the state of the art for MD simulations. So that brings us to our overview of how things are done. First, we have the TLE parameters, which you've done last week. Energy minimization, heating, and equilibration are what you will tackle this week. And then we would proceed to dynamics and, of course, any analysis that is interesting to do. So this is basically how the proceedings go. This will be to decrease the energy in the system. This is assigning velocities, and then this is equilibrating out those particles, given the velocities that they have. So this week in lab, we will be moving on to energy minimization and equilibration of the BPTI, picking up from where you have been working on last week. Alrighty, we do have some presentations today, but I would just like to pause for a moment to ask if anybody has any questions on the simulations.
I had a question that,